This is a quantitative application of Raoult's law. We want to make a solution whose vapor pressure is a bit lower than the pure solvent, 1.5 millimeters of mercury lower than that of the pure solvent, and we're trying to calculate how much solute we need to add in order to get this accomplished. So we've applied our condition that we want our solution 1.5 millimeters lower than the pure solvent. So here's the pure solvent, we subtract 1.5, and this is the target vapor pressure we want for the solution. So we now know what the vapor pressure of the solution is that we want. We know the vapor pressure of the pure solvent. So now we can calculate the mole fraction of the solvent, and from the mole fraction of the solvent, we can back calculate how much solute we need. Right, so we've done so. We now know what mole fraction of the solvent we need to accomplish this lowering, and we need to apply the definition of the mole fraction to calculate how much of our solute we need. We note that we can calculate the moles of the solvent from our initial statement question, because we know we have 320 grams of the solvent. All right, so we calculated the moles of our solvent, which is water, popped that into the equation for mole fraction, and we see we have one equation with one unknown. It's going to involve a bunch of algebra, but we can solve for the one unknown. The first thing I'm going to do is to cross multiply. We have this times this, it's going to equal this times this, and that will allow us to solve for something that's in the denominator a bit easier. Now I'm going to use the distributive property, and on the left-hand side we'll have this times this plus this times this. I'm going to collect like terms by subtracting 16.64 from each side. Now we can solve for N, the moles of sucrose. Our question asks us to solve for the mass of sucrose, so we're going to multiply the formula weight times the number of moles to get mass. We can justify 3 sig figs in our answer, so we express our answer with 3 sig figs, and we're done.